Today I want to talk about limits. And to motivate why we're talking about limits, I want to go back to video 1 for just a second. In video 1, we were calculating the average rate of change on an interval which looked like 1 in the beginning, and then there was some later time. Let me just call that later time x2. What we said yesterday was that, when x2 is large, the average rate of change on this time interval was not a particularly good representation of what was happening in that example, what was happening to the car at this initial time of 1. When we changed that second time to 1.02 and we made the time interval much smaller, we got a much closer representation to the car's actual behavior at time x equals 1. And yesterday I said that one of the ideas of calculus was to take that interval 1 to x2, some later time period, and make that time interval smaller and smaller and smaller, and to let x2 get closer and closer and closer to 1. In this way, we get a progressively better representation of what the car's actual speed was at the time 1. But notice that we cannot let x2 actually equal 1. If we had information about the car's odometer at x equals 1, then we would have a redundancy in our information. We would basically just have one static snapshot of the car's odometer at a single time. And from just the information at the single time, x equals 1, there's no way to get any information at all about the car's speed. So the idea of that average rate of change, trying to get at a progressively better estimate of the car's actual speed, is to let x2 just creep up on the value of 1 to get closer and closer to 1 without ever actually equaling 1. And this idea of letting something get close to a value without ever actually achieving that value, this is the idea of a limit. Limits allow you to get close to something without ever actually touching it. Before we get into that, I need to make sure that we completely understand what it means to use the graph of a function to evaluate a function at a given x value. So let's do a quick review. We have a function f of x, which is graphed in cyan here. So let's use the graph to evaluate each of the following. F evaluated at -1, 3, 0, and -2. If I'm going to evaluate f at -1, the first thing that I'm going to do is I'm going to locate a horizontal position in this picture where x is -1, and that would be right here. Now, looking at this horizontal location, I'm going to try and find a point on the graph that has an x-coordinate of -1. The function's output is the height of the function. The y value is 1. Now this is a process that you're probably familiar with, but where things get tricky is when the graph starts to have strange behavior like these holes here. Let's try and evaluate the function at 3. So I look and I try and find 3 in this picture, and x equals 3 lives right here. So the question is, should I look at this point, or should I look at this point down below? I need to look at the location on the graph that has a filled dot. Holes indicate points on the graph that don't count. If you see a hole in the graph, that means that that exact location is not actually on the graph at all. The real location of the graph when x is equal to exactly 3 is indicated by this floating fill dot down below. That's where the graph actually is. So what's the y-coordinate of that fill dot? The y-coordinate of that fill dot is -1. And therefore the true value of f of 3 is equal to -1. So let's try and apply that principle to f of 0. So I'm going to look on the graph for the locations where x is 0, right here on the y-axis. The true point on the graph is the one corresponding to the fill dot. This point has a y-coordinate of 0, and therefore f of 0 is equal to 0. Now what about f of -2? X equals -2 is located right here, on the far left side of the graph. Now if I look for a location on the graph that has a -2 for the x component, the only possible candidate would be this endpoint right here. But again, there's a hole at this point, and holes don't count. But this time, there's no filled dot in this x equals 2 location that I could use as a substitute for the hole. As a result, the function is actually completely undefined at -2. So we would say that f of -2 is undefined. We might also say that f of -2 does not exist. There is a hole in the graph at -2, and there are no filled dots anywhere else that could be used to make up for that hole. Having reviewed what it means to evaluate a function from a graph, I want to look at the graph of a very specific function. I want to look at the graph of the function sine of x divided by x. Now look at this function in the vicinity of x equals 0. Based on the scale of this graph, it really does seem like if I plug 0 into this function, that 1 should be the result, right? Because if I plug 0 into this function, if I look at x equals 0, follow that to the graph, 1 is equal to the height of the graph at that location. So it really seems like f of 0 should be equal to 1. However, we do have the actual formula for f of x here. And so if we wanted to evaluate f of 0, the easiest and most reliable way to do that would be to actually take 0 and plug it into the formula for x. Now if we do that, we get f of 0 equals sine of 0 divided by 0. And we can already stop right now, because as soon as you get a 0 in the denominator of a fraction, the game is over. You can't divide by 0 under any circumstances, so this definitely is undefined. This definitely does not exist. The issue is related to what we saw at the very end of video 01. The issue is that Desmos, being an expert liar, does not include any holes in the graph. It's just not capable of displaying them. However, limits enter as a way for us to deal with these pesky isolated holes in the graph. And in some sense, limits give us a way not to have to worry about holes anymore. This is the casual idea of a limit. If you're looking at a computerized graph of a function, and it really seems from the graph that f of a should be equal to some number, let's call it L, in that case, we would write LIM. This is for limit. We would put x arrow a underneath that limit. We would write the function's name, f of x, equals L. And here's how we would read this statement. The limit, LIM for limit, the limit as x approaches a, x with an arrow toward a, of f of x is L. In the scenario of sine x over x, we would say that the limit as x gets close to 0 of sine x over x is equal to 1. Because looking at a computerized graph, it really seemed like f of 0 should be equal to 1. And it would be equal to 1 if only there were not this pesky hole in the graph, which is so difficult for computers to properly display. Another way to think about it, if your f of x values get closer and closer to the value L, if you plug in x values that are closer and closer to the value a, then we would again say that the limit as x approaches a of f of x is equal to L. We can check this out using Wolfram Alpha, for example. If I wanted to plug in a number like 0.01 into sine of x over x, notice how close x is to the value 0. When I plug that into the function, I get an output which is extremely close to 1. Now, one really important thing to bear in mind about limits is that limits are concerned only with what is happening near, close to, in the neighborhood of x equals a. If you see the symbols, the limit as x approaches a, f of x equals L, this is saying that f of x is near L when x is near a. Limits absolutely don't care at all about what is happening at x equals a. As a rule, the value of the limit and the value of f of a can be and often are completely different. They are absolutely unrelated to each other. Let's have a look at the function graphed on the right hand side here. Now, I've used colors pretty wildly here, but all of this is part of the same graph of the same function. In this graph, what is the actual value of f of 1? The actual value of f of 1, I need to go on the graph and look at locations where x is equal to 1. Now, there are two possible candidates for points on the graph with this x component. But the point on the top is a hole, and holes don't count. I have to look at the fill dot down here at y equals -1. And so I get the result -1. But when someone asks about the limit, what is the value of the limit as x gets close to 1? What is happening to the function near x equals 1? What does it seem like f of 1 should be based on the behavior around x equals 1? In this situation, what happens at x equals 1 basically doesn't count at all. I should try and absolutely ignore what the function is doing at x equals 1, and I should only consider what's happening nearby x equals 1. Now, nearby x equals 1 are these points here on the left-hand side, here on the right-hand side, which I'm going to indicate with these white chevrons. And if I consider the behavior of the function near x equals 1, it seems like the function's output should be this point at y equals +1. that would be the value of the limit. The limit as x gets close to 1. As x gets close to 1, the y value also gets close to 1. Now, in order to make this idea a little bit more concrete, we're going to have to get started talking about something called a one-sided limit. We're going to introduce two types of notation, two different quantities here. The first one is written LIM for limit, x to a, but what's important about this is above the a is going to be a little minus sign. If you see this notation, we would read this out loud as saying the limit as x approaches a from the left. That's the meaning of this little minus sign. We're going to sneak up on a from the left side from the negative direction. The limit as x approaches a from the left of f of x is L. That's how we read this. What this is saying is that as x literally gets close to the number a from the left-hand side, the y value of the functions, the outputs, begin to get closer and closer to this number L. Now, corresponding to that, we have notation for a right-sided limit. The notation is almost the same, but instead of a minus sign above the a, we have a plus sign. And this has almost exactly the same meaning as the left-hand limit, except now we're creeping up on x equals a from the right side, from the positive direction, from a plus a little something. As x gets close to a from the right, the outputs, the y variables, get closer to this number L. So let's work on finding some one-sided limits for the following function. So first question, what is the value of the limit as x approaches 0 from the right of f of x? What does this equal? So I'm going to go to the graph and I'm going to locate x equals 0. But what's happening at x equals 0 is absolutely irrelevant to me. What I'm going to do is I'm going to look on this picture for locations which are near x equals 0. And in particular, I'm only going to look at points which are to the right of 0. So the location on the graph that I'm looking at in this first problem is indicated by these little pink chevrons that I have drawn on the graph. Now, as I follow the little pink chevrons toward 0, I'm noticing that the y values are getting closer and closer to this y value of -1. Because the y values are getting close to -1, as x gets close to 0 from the right, I'm going to say that the value of this limit is equal to -1. What's happening on the left side does not matter for this question. The fact that there is a hole at x equals 0 does not matter for this question. The limit as x approaches 0 from the right is only concerned with this little region here indicated by these pink chevrons. What's happening close to 0 on the right-hand side of 0. Similar question, but this time the plus sign above 0 has been replaced with a minus sign. This question is asking us to get closer and closer to x equals 0 from the left-hand side, from the negative direction. So I'm going to indicate that region with these green chevrons. On the graph of the function, slightly to the left of 0. Now as I follow those green chevrons, the y values on the graph are getting closer and closer to this y value of 0. So that's the value of the limit. As I follow the green chevrons, closing in on x equals 0 from the left side, y equals 0 is the value that we are approaching. Now in this case, the filled dot happens to live at y equals 0 as well. But that doesn't matter. Limits don't care what's happening at the point, only what's happening near the point. What is the value of the limit as x approaches 3 from the right of f of x? So in this case, I'm going to locate x equals 3, but I don't care what's happening at x equals 3. I only care what's happening near x equals 3 on the right-hand side. So my attention is on these red chevrons. If I follow those red chevrons moving in toward 3 from the positive direction, the y values are getting closer and closer to y equals 0. And therefore, the limit from the right-hand side is equal to 0. What about from the left? From the left side of 3, follow that graph up toward 3, and those chevrons are still pointing me toward a height where y is equal to 0. That's the value of the limit. Now let's creep up on minus 1. So let me approach x equals minus 1 from the right side. If I approach x equals minus 1 from the right side, I'm getting closer and closer to a location where the height is positive 1. So that's the value of the limit from the right side. And once again, it just so happens to be equal to the limit that we get from the left side. We get a value of y equals positive 1 from that approach as well. Now, a word of caution, a common error when students are working on limits is that when you are approaching A, don't start too far away from A. Start pretty close to A. To give you an example, here we have another function, graphed multicolored. All of this is the same function, it's just that the colors got a little wacky. Someone says to me, what is f of 1? We are at x equals 1, and the point on the graph that corresponds to being at x equals 1 has a height of 3. So the value of f of 1, the y value at x equals 1, is 3 units. What is the value when we approach x equals 1 from the right side? So x equals 1 is right here, indicated by the pink arrow, and I'm going to approach x equals 1 from the right side. Now what you don't want to do is start your approach all the way over here. That's way too far away from x equals 1. You want to start very close to x equals 1, almost as close as you can. So I'm going to draw my green chevrons very, very close to x equals 1, approaching 1 from the right side. Now if I follow those green chevrons, following the graph to x equals 1 from the right side, I'm getting closer and closer. In fact, I'm remaining constant at a y value of 2. And therefore 2 would be equal to the limit as x approaches 1 from the positive direction. If instead we approached 1 from the negative direction, then here is x equals 1, here is a little bit to the left of x equals 1. So I'm going to start creeping in on x equals 1, a little bit to the left of that location, and so I need to follow the orange chevrons, and they point up to a y value that's equal to positive 1. Now notice that all three of these values are completely different. Now what about if we did this at f of 2? And I'm looking on the graph, this hole doesn't count, but we do have a fill dot right here. And that fill dot at x equals 2 has a height of y equals 1. If we approach 2 from the right hand side, and I'm going to follow those cyan chevrons in, getting closer and closer to x equals 2, and those chevrons are pointing to a location where the y value is still 1. But if I approach 2 from the left-hand side, indicated by this minus sign, and so I need to follow these orange chevrons. These orange chevrons are pointing to the location where the y value is 2 units. The limit from the left is 2 units. Now so far, we've been dealing with limits and graphs, but you can also do limits when working with a table. Here is a very short table of values for a function f of x. If we try to plug in x equals 0 itself, we won't get a real number answer. F of 0 itself is undefined. But what if we began to approach 0 from the right-hand side? As x approaches 0 from the right-hand side, then what are the y values doing? 4.6, 4.8, 4.999. The y values are approaching 5. And therefore the limit as x approaches 0 from the right is equal to 5. What if we approach 0 from the negative direction? What if we approach 0 from the left-hand side? The y values are going from 7.2 to 7.6 to 7.981. It looks like the y values are getting closer and closer to, what do you think? The y values are approaching 8. So the limit from the left-hand side is 8 units. There are also some situations where, as you follow the graph from either the left or the right side of A, that you don't necessarily get closer and closer to a real number. An example of that would be here. We have the function f of x equals 1 over x minus 1. You might remember from pre-calculus that this function has a vertical asymptote at x equals 1. As a result, f of 1 is undefined. If we tried to plug in x equals 1, we would divide by 0, which is no good. But that doesn't mean that we can't calculate the limit. We can totally still calculate the limits. So someone says, what is the value of this limit? Now pause for a minute and test yourself. Is this asking for the limit from the left? Or is this asking for the limit from the right? There's a minus sign above 1, so we're calculating the limit from the negative direction, which is always on the left. So I'm going to go onto the graph. I'm going to locate x equals 1, which is right here where the vertical asymptote is. And then I'm going to move slightly to the left. I'm going to draw some chevrons from left to right, moving in toward 1. But as we follow those chevrons are pointing straight down toward negative infinity. They're not pointing toward any fixed y value. So what we would write is, we would write that the limit as x approaches 1 from the left side is negative infinity. as we get closer and closer to 1 from the left direction, the y values just keep getting smaller and smaller and smaller. So the limit from the left side is minus infinity. Based on that, what would you say is probably going to be the limit from the right side of positive 1? If I start slightly to the right of positive 1 and move in toward positive 1 along the graph, this time those chevrons are pointing straight up. The closer we get to x equals positive 1 from the right side, the larger the y values become. And so we would say that the right-hand limit is equal to positive infinity. Now, one final technicality before we conclude this video. If you have a limit which is quote-unquote equal to infinity or negative infinity, as in the previous two examples, then technically speaking, the limit does not exist, because infinity and minus infinity aren't actual numbers. So we might say something like, limit as x approaches 1 from the negative direction of f of x does not exist, but can be labeled positive infinity to indicate the fact that as we approach x equals 1 from the right side, that the y values keep getting larger and larger and larger. So that concludes today's material. We talked about why we might be interested in a limit. We looked at how limits can be calculated from graphs and from tables. And then we looked at the specific case where a limit might be equal to positive or negative infinity.